Welcome to our lecture on parental care in amphibians. Think about how human parents spend years feeding and protecting their children. While many animals simply lay eggs and leave, some remarkable amphibians act much more like us, investing incredible energy to keep their babies safe. Let us explore how and why they do this. Now that we have introduced the topic, let us define what this behavior actually is. In biological terms, parental care in amphibians is any action taken after the eggs are laid that increases the survival probability of the offspring. Instead of making thousands of unprotected babies and hoping for the best, these dedicated parents choose quality over quantity, ensuring a select few have a much higher chance of reaching adulthood. This fascinating behavior is a vital evolutionary adaptation. This dedication, however, does not come for free. Providing this care comes at a massive physical and energetic cost to the parent. By staying behind to guard or carry their young, these amphibians often cannot hunt for food or find another mate for the rest of the season. It is a heavy sacrifice, but one that pays off in the survival of their lineage. By investing their limited biological resources into a small number of offspring, they dramatically increase the odds that their specific genetic material will be passed on to the next generation. You might be wondering, why is this so crucial for amphibians specifically? The answer lies in their biology. Amphibians lay anamniotic eggs, meaning they lack a hard, protective outer shell. This makes them incredibly vulnerable to drying out, fungal infections, and hungry predators. By evolving parental care, these species can survive in harsher, unpredictable environments like fast-flowing streams or dry land, where unguarded eggs would instantly perish. Before we look at the math behind this, let us see some real-world examples of these amazing behaviors. The male midwife toad literally wraps strings of fertilized eggs around his hind legs, carrying them everywhere. The Suriname toad has eggs that sink right into the spongy skin of the mother's back to develop safely. And the Darwin's frog male actually swallows his tadpoles, raising them safely inside his vocal sac until they are ready to emerge as fully formed miniature frogs. These diverse strategies highlight how adaptable amphibians can be when it comes to protecting their vulnerable young. To truly understand this evolutionary trade-off, we can use a mathematical model. This formula calculates the net reproductive success. S is the number of surviving offspring. N is the total eggs laid. P0 is the tiny base chance of survival without any care. Alpha represents how effective the care is, and C is the actual energy or time invested by the parent. As the investment C increases, the overall survival probability goes up significantly. However, the parent usually has to decrease the total number of eggs, N, because they only have a limited amount of biological energy to spend during a single breeding season. Now that we have our formula, let us apply it to a real scenario. Consider the common frog. This species lays 2,000 eggs, but provides absolutely zero parental care, so C is 0. The base survival chance is just 1%. Plugging these into our equation, the care term completely drops out. Multiplying 2,000 by 1% reveals that only 20 tadpoles will survive to adulthood. The vast majority are lost to the harsh environment. Let us compare that to the poison dart frog. This parent lays only 40 eggs but invests heavily, providing 10 units of care with an effectiveness of 0.08. The base survival is the same. When we calculate the enhanced survival probability, the care adds a massive 80% boost. Multiplying the 40 eggs by an 81% survival chance gives us approximately 32 surviving offspring. Even with far fewer eggs, this dedicated care yields more surviving adults. We can also use this model in reverse. Suppose a male Darwin's frog wants exactly 15 offspring to survive from a clutch of 20 eggs. The base survival is 0.05, and his care effectiveness is 0.07. We plug these known values into our equation and use basic algebra to isolate C. Dividing by 20, subtracting the base rate, and dividing by the effectiveness shows he must commit exactly 10 units of care, meaning weeks of fasting while carrying tadpoles, to reach his goal. Having just solved for the required investment numerically, let us prove how we can derive a general formula for C that works for any species. We start with our standard survivorship equation. Our goal is to isolate the parental care variable, C. The first logical step is to divide both sides by n, the total number of eggs. This gives us the required overall survival probability on the left side, which must equal the base probability plus the added benefit of parental care. Understanding this setup is crucial before we isolate our target variable. Continuing our derivation, we now need to remove the base survival rate from the right side. We subtract P0 from both sides. This isolates the survival boost that must come strictly from the parent's efforts. Finally, we divide the entire left side by alpha, the effectiveness coefficient. This yields our final proven result, a universal formula to calculate the exact biological energy or time a parent must invest to achieve a specific reproductive target in any environment. You can now see exactly why the math dictates such intense physical demands on these adult amphibians. This brings us to a visual summary of the two distinct evolutionary paths we have discussed. On the left side of this diagram, you see the high-quantity, low-care strategy. The parent abandons a massive cluster of eggs, leaving them highly vulnerable to the predators shown nearby, resulting in very low survival. On the right, you see the low-quantity, high-care strategy. The parent physically carries a small clutch of eggs, shielding them from harm. This direct investment ensures a much higher proportion of the offspring successfully develop into froglets. To wrap up our lecture, let us review the most important ideas. Parental care in amphibians is a vital adaptation that shifts the reproductive strategy from quantity to quality. By guarding or carrying their young, parents counteract the severe vulnerabilities of their shell-less eggs. As we proved with our mathematical model, investing deeply in a few offspring often yields a higher net reproductive success than blindly producing thousands. Ultimately, this incredible dedication is what allows these species to survive and thrive in some of nature's most challenging environments.